Hi, I'm Mark Ciampach, the author of Security Plus Guide to Network Security Fundamentals, 4th edition. In this lecture video, we will talk about Chapter 7, Administering a Secure Network. In the previous chapter, we looked at building a secure network through network devices, network technologies, and the design of the network. But properly administrating a secure network is also critical as well. In this Chapter 7, we will discuss common network protocols, network administration principles, and how to secure network applications. Remember, stay secure. Chapter 7, Administering a Secure Network. Security Plus Guide to Network Security Fundamentals, 4th edition. Here are the objectives that we're going to be covering in Chapter 7. By the time we're finished, we want to be able to list and describe the functions of common network protocols. We want to explain how network administration principles can be applied. And we want to define the new types of network applications and how they can be secured. Let's begin by talking about common network protocols. By definition, a protocol is simply a rule of conduct and communication. Protocols are used all the time when we think about ceremony and etiquette in foreign nations. Those visiting foreign nations have to be sure that they follow protocol, that is, the ceremony, the etiquette that is used in a nation that is different from what they may be used to. By the same token, we have protocols for computer networks as well. These are simply rules for communication, once again. Transmission Control Protocol / Internet Protocol, TCP/IP, is the most common protocol suite that's used for both local area networks as well as for the Internet today. Although TCP/IP, the suite, is composed of different protocols, the two major protocols that make up its name, IP and TCP, are considered the most important. IP is a protocol that functions primarily at the OSI, Open Systems Interconnection, network layer 3. It provides addressing and routing. TCP is a transport layer, that is layer 4 protocol, that's responsible for establishing connections between devices and making sure that we have reliable data transport. Now, TCP/IP itself uses a 4-layer architecture: network interface, internet, transport, and application. And this figure shows us a comparison between the OSI model and the TCP/IP model. The TCP/IP architecture really gives us a framework for dozens of different protocols that actually make up this suite. These include high-level protocols that are part of TCP/IP, like Telnet and File Transfer Protocol. Now, some of the basic TCP/IP protocols are Internet Control Message Protocol, ICMP, Simple Network Management Protocol, SNMP, Domain Name System, DNS, and File Transfer Protocol, FTP. And there also, of course, is the new version of IP, which we've all heard about, IPv6, which is designed to replace our current version, IPv4. Let's drill down and take a look at each one of these. We'll begin by talking about ICMP. We've mentioned ICMP in a previous chapter regarding how attackers use command and control systems. But ICMP is one of the core protocols of TCP/IP. It's used by devices to communicate updates or error information to other devices. These messages can be sent as a result of perhaps basic errors, maybe requests for service that was not available, or more advanced situations. Maybe a gateway doesn't have the buffering capability to forward a packet. So ICMP is also used to relay query messages as well. Each ICMP message contains 3 fields: a type, a code, and a checksum. The type field is 8-bit. It identifies the general category of the ICMP message. For instance, a type 3 is a destination unreachable. Type 12 is a parameter problem. there are actually 13 different type values. The code field gives us some additional information regarding the type field. And the checksum is a field that's used to verify the integrity of the information. This table shows us some common ICMP code values for type 3, destination unreachable. Remember we said that we've got our type field, and then our code field gives us some specific information about that type field. And these are the code values for a type 3. We can see the added info that it gives to us. Now there are several attacks that try to take advantage of ICMP. One is network discovery. An attacker could use an ICMP message as one of the first steps in reconnaissance to uncover information about the hosts that are part of that network. This might include sending individual ICMP echo requests to the broadcast address of the network and sending an ICMP address mask request to a host on the network to determine what the subnet mask is. There's something called a Smurf DOS, denial of service attack. Attackers can broadcast a ping request, and this is part of ICMP, to all computers on the network, but change the address from which the request came to that of a target computer, so that when all the computers respond, they actually respond to that target computer, the one being attacked. ICMP redirect attack is sent to the victim that asks the host to send its packets to another router, but this router is actually a malicious device. And the ping of death, a malformed ping using ICMP is sent to the victim's computer that exceeds the size of an IP packet, and this may cause the host to crash. So there are a variety of attacks that can use the ICMP protocol. Let's move on to SNMP, Simple Network Management Protocol. The Simple Network Management Protocol was introduced back in 1988, and it's supported today by almost all networking equipment manufacturers, and it's a very popular protocol for managing network equipment. It allows network managers to remotely monitor and manage and configure devices on the network. Now, SNMP really functions by exchanging management information between network devices. And SNMP is not just found on core network devices anymore, but it also can be found on a printer, a fax machine, even a UPS, uninterruptible power supply. Now, each SNMP device has to have an agent or a service that listens for commands and then executes them. These agents are protected with a password, and this password is called a community string. That's, of course, to prevent unauthorized users from taking control over an agent. And there are two types of community strings. A read-only string will allow information from the agent to be viewed, while a read-write will allow the settings on the device actually to be changed. There were, unfortunately, several security vulnerabilities with the use of community strings in the first two versions of SNMP, known as SNMP v1 and SNMP v2. The default SNMP community strings for read-only and read-write were public and private, not very secure there. And administrators who didn't change these default strings could be left open for an attacker taking control of the device. Also, the community strings were transmitted in the clear, were not encrypted at all, so an attacker with a protocol analyzer could, again, view the contents of the strings. Because of these different vulnerabilities, SNMP v3 was introduced back in 1998, and SNMP actually uses usernames and passwords along with encryption. Domain name system. We've spoken about the domain name system previously. Domain name system is a TCP/IP protocol that resolves an IP address to its equivalent symbolic name. So we're mapping 69.32.148.124 to www.course.com. And the DNS is a database organized as this inverted tree hierarchy so that the name of each site and its corresponding number can be resolved. Now, to store the entire database of names and IP addresses in one location would obviously cause many problems. It'd be a bottleneck and slow down everybody using it. And if something were happening to this database, then the entire domain name system would be infected. So, instead of being on just one server, a DNS database for the internet is divided and distributed to many different servers, each of which is responsible for different areas on the internet. And here is an example of how this DNS functions when I have multiple servers serving those individuals who are looking for the resolution. Very quickly, in step 1, the request for the IP address of a site, www.nashville.com, goes to the user, from the user's computer rather, to the local DNS server that's part of the local area network to which it's connected. In step 2, the local DNS server says, oh, I don't know the IP address of www.nashville.com. But you know what? It does know the IP address of a DNS server that contains the top-level domains and their IP numbers. So a request is sent to this top-level domain DNS server. In step 3, the top-level DNS server sends back the IP address of the DNS server that contains information related to addresses that end in the top-level domain.com. So the local DNS server then sends a request to the second DNS server that contains the IP address of the DNS server that contains information about Nashville.com. And then in step 4, after receiving back that information, the local DNS server contacts the third DNS server that's responsible for Nashville and looks up the IP address of www.nashville.com. And this information in step 5 is finally returned to the local DNS server that sends it back to the user's computer. So just a little bit of information there about how this DNS system works. It's always running in the background there for us, and we use it all the time whenever we're out on the internet, but we often fail to recognize how valuable it is, but also what goes on behind the scenes. Now, just like ICMP, DNS likewise can be the focus of attacks. It's pretty obvious that DNS plays such an important role today. Certainly it's going to be the focus of attacks. One type of attack is DNS poisoning, when we've mentioned this previously. DNS poisoning substitutes addresses, so the computer is automatically redirected to another fraudulent device. An attacker substitutes an IP address for a symbolic name, and then substituting this fake IP address can be done on either the local host table or the external DNS server. Now, DNS poisoning can be prevented by using the latest editions of the DNS software, which is known as the Berkeley Internet Name Domain, which we abbreviate BIND, B-I-N-D. These latest versions make DNS servers less trusting of information passed to them by other DNS servers and can ignore any DNS records that are not directly related to the query. And there's even a newer secure version called the Domain Name System Security Extensions, DNSSEC, that uses even more advanced measures. A second attack using DNS is really kind of a reverse of the DNS poisoning. Instead of sending a zone transfer to a valid DNS server, the attacker instead asks the valid DNS server for a zone transfer, called a DNS transfer. When the attacker has this information, it might be possible to map the entire internal network of the organization that supports that DNS server. File transfer protocols. Prior to the development of the World Wide Web and HTTP, the Internet was used primarily for transferring files from one device to another. And there are different protocols that were used for transferring files. The File Transfer Protocol, FTP, and Secure Copy Protocol, SCP. We'll begin by talking about FTP. Transferring files is performed most frequently under FTP. FTP is an unsecure TCP/IP protocol. It's used to connect to an FTP server, much in the same way that HTTP links to a web server. There are several different methods for using FTP on a local host computer. You can use a command prompt. You can open up your web browser. You can download and use a separate FTP client. But using FTP behind a firewall can present several different challenges. FTP typically uses two ports. TCP port 21 is the FTP control port for passing FTP commands, and TCP port 20 is the FTP data port through which data is sent and received. Now, using FTP active mode, an FTP client initiates a session to a server by opening what's called a command channel connected to the server's TCP port 21. A file transfer is requested by the client by sending a command to the server, which then attempts to initiate a data channel connection back to the client on TCP port 20. However, the firewall may see this data channel connection request from the server as something that's unsolicited and drops the packets. This typically can be avoided by using something called FTP passive mode. What we just described was actually FTP active mode. In passive mode, the client initiates a data channel connection, but instead of using a specific command called PORT, the client sends a PASV command on the command channel, and the server then responds with the TCP port number that tells the client which connection to use, which port to use for that data channel. And it's usually anywhere from port 1025 to port 5000. Here's an example of an FTP client. Now, just like DNS and ICMP, there are security issues related with FTP. First and foremost, FTP does not use any sort of encryption. So usernames, passwords, files that are transmitted are all done so in clear text. So again, an attacker who's nosy could be able to access that information using their protocol analyzer. In addition, files being transferred by FTP are vulnerable to man-in-the-middle attacks. Data could be intercepted and altered before it is sent on to the destination. Well, the solution then is twofold, two different options. One is to use something called FTP using secure sockets layer. That's quite a mouthful. Anyway, abbreviated FTPS. As the name implies, it uses SSL TLS, secure socket layer, transport layer security, to encrypt commands that are sent over the control port in an FTP session. FTPS is a file transport layer that really sits on top of SSL and TLS so that the FTP protocol to transfer files to and from FTP servers are SSL enabled. There is a weakness of FTPS that although the control port commands are encrypted, the data port may or may not be encrypted. A second option is to use secure FTP, and this is SFTP. And there are several differences between SFTP and FTPS. It gets confusing with all of these letters, although they're still fairly similar. FTPS is a combination of FTP and SSL TLS. SFTP is really an entire protocol itself. And SFTP only uses a single TCP port instead of two ports, like FTPS. And finally, SFTP encrypts and compresses all data commands, whereas FTPS may not encrypt the data. So there are some significant differences. We can simply say that secure FTP, SFTP, is preferable over Secure Sockets Layer, FTPS. Now, another protocol that can be used for file transfers is something called Secure Copy, SCP. This is really an enhanced version of the Remote Copy Protocol. SCP encrypts files and commands, so it sounds good, but it does have a few limitations. File transfer cannot be interrupted and then resumed in the same session. If there's a problem, session has to be terminated and then it has to be restarted. And SCP is mainly found on Unix and Linux platforms, not so much on other platforms with which we might be familiar. The current version of IP is IPv4. It was developed way back in 1981, long before the Internet was universally popular. And as we might expect, IPv4 has several weaknesses associated with it. One weakness is the number of available IP addresses. Because the IP address is 32 bits in length, there are only about 4.3 billion possible addresses, and that's not enough anymore for all of the devices that we all are carrying around with us. Another weakness is that of security. Really, due to its structure, IPv4 can be subject to different types of attacks, actually several different types of attacks. So the real solution, long term, is the next generation of the IP protocol, which is called IPv6. IPv6 addresses the weaknesses of IPv4, and it provides several other significant improvements. Here is a comparison between the IPv4 header and the IPv6 header. Just looking at these can show some of the differences between the two, and that IPv6 has several enhancements over IPv4. Now, the security enhancements that IPv6 has is that cryptographic protocols are really part of the core protocol that supplies secure data communications, and there are new authentication headers that prevent IP packets from being tampered with. That's all good. The number of IPv6 addresses, in case you're interested, increases from 4.3 billion under IPv4 to something like 340 trillion addresses, or 665 million billion IP addresses per square meter on Earth, something like that. So we probably won't run out for a while. Yes, and here's a comparison of the IPv4 and IPv6 headers. There are several differences there. IPv6, however, has been very slow to be adopted. Just about every year you can read an article that says this is the year of IPv6, when there'll be mass migration to it, but that just has not happened. And so, not exactly sure when this mass migration to IPv6 will occur. We'll just have to wait to see. Let's now move our attention to network administration principles. It's obvious that administering a secure network can be a difficult task. Administering a network is hard enough, but administering a secure network can be difficult. It's important that network security administration follow what's called a rule-based approach. This is a process of administration that relies on following procedural and technical rules, instead of just creating security elements on the fly to fix an emergency. There certainly are different types of rules. A procedural rule is defined as an authoritative and prescribed direction of content. Procedural rules dictate technical rules, and technical rules may involve certain things as actually configuring the firewall or the proxy server in order to follow the procedural rules. So obviously, technical rules shouldn't dictate procedural rules, but it should be the other way around. It's the role, of course, of the network administrator to follow a rule-based management approach. This involves following the technical rules about device security as one example. Because new devices are continually added to the network, securing devices never ends, but it's a very important role. Device security would include such things as secure router configuration, flood guards, and analyzing device logs. Let's talk about secure router configuration to begin with. Of course, one of the most important appliances on the network today is that of the router. As we said before, routers operate at the layer 3, the network layer of the OSI model, and it forwards packets across computer networks. Routers can also perform a security function because packets go through the router. The router can be configured to filter out specific types of network traffic. Here's an example of basic secure router configurations. If I want to create a design, if I want to use a meaningful router name, securing all ports, setting strong administrator passwords, making changes from the console, how should I do that? So these are just some of the basic things in keeping a router secure. Yes, and this figure illustrates for us a network that shows how a router kind of fits into the picture, if you would. Now, one of the dreaded attacks that is feared by most web servers is that of a denial of service attack or even a distributed denial of service attack. One type of denial of service attack is a SYN flood attack. We've talked about this back in Chapter 2. It takes advantage of the procedures for initiating a session. Now, there is something called, as a defense against these attacks, flood guard. A flood guard is a feature that controls a device's tolerance for unanswered server requests, and then that serves to prevent a denial of service attack. A network administrator can set the maximum number of developing connections that the device will tolerate. And once that limit is reached, each inbound SYN is directed to the affected server, is intercepted and dropped, and any sort of empty SYN plus ACK packet is in return. So flood guards are typically found on firewalls, intrusion detection systems, and intrusion prevention systems. Log analysis. We've mentioned before that a log is a record of events that occur. Logs related to computer security, have become very important, and monitoring these logs is very useful in determining maybe how an attack occurred or whether it was successful. And logs for system security on hosts can be broken into two camps: operating systems logs and typically security application logs. Now, network security hardware devices also generate logs that reflect the entire network. So if the network hardware device is a security-related device, like a firewall or an IDS, the log file can reveal specific security-oriented information. Yet if the device is a standard network device, then standard logs simply are analyzed. Some of the types of security hardware logs that can be generated: network intrusion detection and network intrusion prevention systems. These can contain detailed logs on suspicious behavior as well as any attacks that might be detected. The domain name system logs, log entry of all queries that are received, proxy servers logs, firewall logs, etc. So each of these logs in and of themselves can contain some important information. Here's a list of the type of information that might be found in a DNS detail log. Information that might be found on a basic firewall log. Here's the information that might be found on a detailed firewall log. Now, it's good to examine these firewall logs because they contain information that can be very helpful to us in examining the security posture as well as adjusting our security on the network. For instance, it could list IP addresses that are being rejected and dropped, list probes to ports that have no application services running on them, source routed packets, suspicious outbound connections, unsuccessful logins. This is all information that could be contained on a firewall hardware log, and this information could be, again, helpful to us. In addition to device security, several network design management principles should be followed to make sure that the security of the network is properly maintained. There are several under this category. We'll first talk about network separation. It's not uncommon as a network grows, we simply need to reconfigure it to provide adequate security. And this is important to maintain or provide network separation so that certain parts of the secure network can't communicate with other parts, to prevent network bridging, maybe prohibiting an order entry network segment from accessing the human resources segment. Now, one way to provide network separation is to physically separate users by connecting them to different switches and routers. Now, this prevents bridging and even prevents a reconfigured device from allowing that connection to occur. There's also something known as air gap. This was introduced in the early 2000s. If I've got two servers, one faces the external internet and the other faces the internal secure network, if they're connected by what's called a single air gap switch, which was only connected to one server at a time. So when a packet arrived from the internet, the server passed it on to the switch stripped the TCP header, stored the packet in memory, and disconnected from the internet server. It then connected to the internal server and forwarded the packet. The header was recreated before the packet was sent out to the internal LAN. Now, the process, of course, was reversed for outgoing packets. This physical separation of networks, which is called the air gap itself, and the stripping of headers was designed to improve the security by removing some potential vulnerabilities. But as you probably have guessed by now, saying, what in the world is air gap? I've never heard of it before. Air gap never caught on and certainly was not and has not been widely implemented at all. Loop protection. We're going to look back at figure 7-8 for a moment. There we go. And in this figure 7-8, the host Z, which is connected to switch A, wants to send frames to host X on segment number 2. Now, switch A doesn't know where host X is located, so it floods the network with the packet. Packet travels down segment 1 to switch B and segment 2 to switch C. Switch B then adds the host Z to its lookup table that it maintains for segment 1, and switch C also adds it to its lookup table that it maintains for segment 3. Yet if switch B or C has not yet learned the address of host Z, they will both flood segment 2 looking for host X. So really what we're saying is each switch will take the packet sent by the other switch and flood it back again because they're not sure where host X is located. So switch A will start receiving packets from each segment and flood it back on the other segments. So we've got a switching loop here, which is causing a broadcast storm as the frames are broadcast, received, rebroadcast, received, rebroadcast. And these broadcast storms can certainly cripple a network just in a matter of really just a few seconds at all. Now, loop protection can prevent broadcast storms. Loop protection is based on an IEEE 802.1d standard, the spanning tree algorithm, STA. STA can determine that a switch that has multiple ways to communicate with a host and then determine the best path while blocking out the other paths. So STA determines the best path, but it also registers the other path in the event that that primary path is unavailable. So STA can determine that a switch has multiple ways to communicate with a host. It'll figure out the best path and block all the other paths. VLAN. We have mentioned before that we can segment a network by physical devices that are grouped into logical units through a virtual LAN, a VLAN. So we can have different users logically grouped together, even though they may be attached to different switches. So that's going to reduce network traffic and provide a degree of security for us. There are some general principles for managing VLANs. A VLAN shouldn't communicate with another VLAN unless they're both connected to a router. We should configure empty switch ports to connect to an unused VLAN. That's a good security step to take. Different VLANs should be connected to different switches. We should be able to change any VLAN default names. And we should want to configure the ports on the switch that pass tag VLAN packets to explicitly forward specific tags. And VLANs should be configured so that public devices like a web app server should not be on a private VLAN. So users will not have to have access to that VLAN. Something very obvious, at least it should be obvious, is securing ports. That's an important step in network management. And ports can be secured through simply disabling unused ports, using MAC limiting and filtering, and through the IEEE 802.1x. We'll talk about each one of those. Let's disable unused ports. Certainly turn off ports that are not required for a network device, maybe unused ports on a switch. Unfortunately, this is simply a step, although very basic, that is often overlooked. MAC limiting and filtering. In addition to disabling unused ports on a switch, we also can use MAC limiting and filtering. This filters and limits the number of MAC addresses allowed on a single port. A port can be set to a limit of 1 and also a specific MAC address assigned to that port. This enables only a single host to connect to that port. If the host is not listed that attempts to access the interface, results in a security violation. Here's an example of some MAC limiting and filtering configuration options. We can set it as static, as dynamic, or as what's called sticky. .1x. This is a IEEE standard that provides really the highest degree of port security. This standard provides security on a port-based authentication scheme. 802.1x blocks all traffic on a port-by-port basis until the client is authenticated using a credential server. Using credentials on an authentication server. I'm sorry, it's an authentication server. I said credential server. This prevents an unauthenticated device from receiving any network traffic until it is accepted into the network. It strictly limits access to the device that provides the authentication to prevent an attacker from reaching it. Here's how IEEE 802.1x works. In step 1, the device, called a supplicant, requests from the authenticator permission to join the network. In step 2, the authenticator asks the supplicant to verify its identity. In step 3, the supplicant sends identity information to the authenticator. And then in step 4, the authenticator doesn't do the authentication, but it passes the identity credentials to the authentication server, whose only job is to verify the authentication of the device. Identity then is sent, information is sent in an encrypted form. In step 5, the authentication server can either reject or accept the supplicant's identity. Then it returns that information to the authenticator. And step 6, if it's approved, the supplicant can now join the network and begin to transmit data. Securing network applications involves looking at some new types of network applications that require security considerations. These new type of applications include virtualization and IP telephony and cloud computing. So we're talking about securing network applications, and some of these applications are a little new. Virtualization. By definition, virtualization is a means of managing and presenting computer resources by function without really any regard to their physical layout or their location even. Computer storage devices can be virtualized in that multiple physical storage devices can be viewed as a single logical unit. Now, one type of virtualization in which the entire operating system is simulated is what we call operating system virtualization. With operating system virtualization, a virtual machine is simulated as a self-contained software environment on a host system, that's the native operating system to the hardware, yet it appears as a guest system, that's a foreign virtual operating system. For example, a computer that normally boots to Windows 7, the host, could run a virtual machine of Linux, which is the guest. There are several advantages to running virtualization. One is for testing. Latest patches, for instance, could be downloaded and run in a virtual machine to make sure that the impact on other software or even hardware is not negative. And we do this before installing the real patches on our production systems. In addition, penetration testing can be performed using a simulated network environment on a computer using multiple virtual machines. One virtual machine can virtually attack another virtual machine on the same host system to look for vulnerabilities. And yet another advantage is host operating system virtualization can be used for training purposes instead of the expense of installing an actual network to set up defenses and create attacks. It can all be done through a virtual system. Now, creating and managing multiple server operating systems is known as server virtualization. Server virtualization relies on something called a hypervisor, and that's software that runs on the physical computer to manage one or more virtual machine operating systems. Now, like the host operating system virtualization, server virtualization has several advantages. One of the primary advantages is that of reducing costs. Not only do I have to purchase fewer physical servers, but in addition, the electricity to run these servers can likewise be reduced because I have fewer physical servers, but I am virtualizing them on one server. Again, we don't have to have as much power. It's estimated that your typical server only utilizes 20% of its capacity, so we certainly have excess capacity on each physical server that I could run multiple virtual machines. Another advantage of server virtualization is it can be beneficial in providing uninterrupted server access to users. Of course, data centers have to have some downtime to perform maintenance, but with mobility and unlimited access that users demand today, it's difficult to find the time to bring a server down that won't impact somebody. So this can be addressed by virtualization. and live migration. The live migration technology enables a virtual machine to be moved to a different physical computer that doesn't going to impact anybody, because the virtual machine stores its current state on a shared storage device immediately before the migration occurs. Virtual machine is then reinstalled on another physical computer. It accesses its storage, the state it was, the information that was saved. No noticeable interruption to users. So we have several advantages there as well. However, for every advantage, of course, there are concerns or disadvantages. Let's list a few of the virtual server and virtual operating system security disadvantages. Physical security devices are not always designed to protect virtual systems. I may have a physical firewall out there, but it may not be able to inspect and filter the traffic that comes from a hypervisor that's running multiple virtual servers. In addition, because live migration allows a virtual server to be moved from one hypervisor to another with simply a click of a mouse, got to have security in place to accommodate this transfer. Unless we're careful, moving virtual machines to another physical machine through live migration could leave virtual servers unprotected if we haven't planned in advance for them. Not all hypervisors have the necessary security controls to keep out determined attackers. And obviously, if a single hypervisor is compromised, consider all the virtual servers that would be at risk. Existing security tools like antivirus, anti-spam, IDS, again, were designed for single physical servers, and sometimes they don't adapt well to multiple virtual machines. Some security tools are external physical appliances that are designed to protect one or more physical machines and not multiple virtual machines. And virtual machines must be protected not only from the outside world, but from other virtual machines on the same physical computer. Now, in a network without virtual machines, I can have external devices like a firewall and an IDS, and it sits in between the physical servers to prevent one physical server from infecting another internal physical server. Yet often there is no physical sort of device that I can have between these virtual machines. So those are some issues to consider. Here we have listed a list of some of the basic features of virtualization. IP telephony. We're changing communication from analog to digital, obviously, and this change has brought with it a completely different way of looking at what occurs behind the scenes. The change is really an effort to unify different types of communication into a single mode of transmission, having an all-digital technology infrastructure. One of the most visible is that of a convergence of voice and data over a single IP network. By using IP, there are various services that can be multiplex, that is, combined together. So IP telephony is a term for using a data-based network to add digital voice clients and new voice applications onto the IP network. There are many advantages to IP telephony. Cost is one. The cost of these convergence technologies is quite low compared to the startup cost for traditional new telephone equipment. Incoming calls can be selectively forwarded or blocked. In terms of management, instead of having a separate voice and data network, it's all one. New applications can be developed more quickly with fewer resources and on a lower cost. And the infrastructure requirements are fewer. There may not be as many regulatory requirements, since local telephone exchanges have regulations they must adhere to, not the same as my internet protocol-based network, and I can have some increased user productivity as well. Yet there are vulnerabilities. We can see the vulnerabilities of IP telephony listed in this table. Soft phones that operate on standard PCs may be vulnerable to operating system attacks. In addition, many parts of the voice over IP protocols may not adequately protect call party authentication. There's no encryption, generally speaking. Attackers could flood a voice over IP target with denial of service type attacks. And actually spam over internet telephony can carry unsolicited sales calls and other nuisance messages as well. And the last new technology that needs to be considered in terms of security is something that we hear kicked around all the time, but sometimes its definition is a little muddy, and that's what's known as cloud computing. Cloud computing is a model for enabling convenient, on-demand network access to a shared pool of configurable computing resources. These resources could be network, servers, storage applications, etc. This can be rapidly provisioned, ramped up, and released, cut back, with minimal management effort or service provider interaction. That is to say, cloud computing is essentially on-demand network access to shared resources that can be scaled up or back very easily and quickly as the demand requires. Now, cloud computing can be understood when it's compared to something known as hosted services. When we compare the two, we'll see the differences between them. Many times when people talk about cloud computing, they're actually referring to hosted services. Now, in hosted services, we've got servers, we've got storage, we've got the networking infrastructure. These are shared by multiple users, and they use remote network connections. And what's significant is these services have been contracted for a specific period of time. I'm going to have a contract for this service for 24 months. Now, as things change, and perhaps I need more resources, maybe I need additional storage space or more computing power, what happens then, I must contact the hosted service. I have to negotiate an additional fee and probably sign a new contract for all of those new services. Cloud computing, on the other hand, is much different. With cloud computing, as my needs increase or they may decrease, cloud computing resources can be quickly scaled up or down. Give me increased resources, decrease the resources I need. And they're done automatically. I don't have to sign new contracts. So by saying on-demand self-service, the consumer can automatically increase or decrease the computing resources. Universal client support. Almost every network device can access these resources. Invisible resource pooling. The physical and virtual computing resources are all pooled together and they serve multiple and simultaneous consumers. They're dynamically assigned and they're reassigned. I, as a customer, have really little or no control over what physical resources I'm using, and I don't really even care as long as I'm getting the resources that I need. Immediate elasticity. Again, the computing resources are elastic. They can be increased, they can be decreased quickly to meet demand. And the services are metered. That is, fees are based on the resources that are being used. Someone has likened cloud computing much to like a utility, kind of like electricity, if you would. The more I use, the more that I am charged, but I don't have to call up the local power provider in advance and say, hey, I'm going to need X number of kilowatts next month as opposed to this month. It's just the more that I need, the more that I use, and the more that I'm charged. Now, there are some variations within cloud computing. That is to say, not all cloud computing is the same. There basically are three service models, if you would. The first is cloud software as a service. The cloud computing vendor provides access to the vendor's software applications that are running on the cloud infrastructure. And all of these applications, which can be accessed just through any web browser, don't require any installation or configuration or upgrading or management from me, the user. This cloud software as a service, the vendor, the cloud computing vendor, is providing this access to me at a fee, yet I can increase or scale back as necessary. Now, a second model is cloud platform as a service, where in this model, I, the consumer, can install and run my own specialized applications on the cloud computing network. And although I have some control over the deployed applications, I don't manage or configure anything at all. That's all taken care of by the cloud vendor. And the third model is cloud infrastructure as a service. Here I do have a higher level of control, actually the highest level of control. Cloud computing vendors allow the customer to deploy and run the customer's own software, which might include operating systems and applications. So in that case, the customer then does have some control over the operating system and storage and their installation. But again, I don't have to manage or control the underlying cloud infrastructure. Let's look at what we've talked about in Chapter 7. We've talked about TCP/IP and said it's the most common protocol for LAN and the Internet. And we've looked at protocols within TCP/IP for transferring files. We've talked about FTP, FTPS, SFTP, and SCP. We've looked at router configuration, that it must provide a secure network environment. We've talked about how flood guards can defend against denial of service attacks. We said that networks can be configured to provide separation and increased security, and should be. We've looked at securing ports as an important step, and we've talked about new network applications that have special security considerations: virtualization, IP telephony, and cloud computing, to name three. Our objectives in this chapter have been to list and describe the functions of common network protocols, to talk about how network administration principles can be applied, and to define the new types of network applications and how they can be secured. Chapter 7, Administering a Secure Network, Security Plus Guide to Network Security Fundamentals, 4th edition.